Okay, so solve each of the following equations in degrees. We know it's degrees because it's 0 to 360, and we've got 3 equations to do. Actually, there are 4. So 1. Sine x is 0.848. I am going to go straight to my Aurora AX595 and do inverse sine or shift in sine. I'm in degrees. What was the thing? 0.848. It's not working. This is another slick video from Maths Dave. 57.99. Okay, we're going to go straight to our favourite cast diagram. Caterpillars attack slimy toads. It's toad carnage. And we mark it in there, 57.99. It's in the A quadrant and the S quadrant, because it was sine and it was positive. So we mark it there as well. So our second value is whatever we get if we do 180 minus 57.99. And so we're going to leave our answers to 3 significant figures as 58.0 degrees and 122. Oh no, just 122 degrees. Okay, question 2. 2 cos 2x equals 1. This question, we've got a great opportunity to get this utterly wrong to start with. We must do inverse cos too soon, must we? Before we do anything else, we've got to get it so it's 1 cos. So cos 2x is equal to half, divided by the 2. Now we're going to do inverse cosine cos to the minus 1 of a half. The calculator says 60 degrees, wasn't it? I don't know who said that. Go to the cast diagram. Cheese and salami toasty is not what I had for lunch today. And we mark that in there. This is cos and positive, so it's going to be A and C quadrants. There it is, 60 degrees, 60 degrees. So as we go around our cast diagram, we get, that would be 300, wouldn't it? There it goes. So there. Aha, but it's 2x. And if x is between 0 and 360, then 2x is between 0 and 720. So we have to go around the cast diagram twice. So as we kept going past the 300 plus 360, that would take us to 420 degrees. And if we keep going around the cast diagram past 420, we scoot on past 540 over there, and get eventually to 660 degrees, just before we finish our rotation at 720. So they're the values of 2x, so x is half of each of those, 30, 150, 210 and 330 degrees. Excellent. 3 marks we gave you for that. Then we come on to part 3, sine 3x equals 1. Well, we start as 1 sine 3x, so we can go straight to the calculator, but actually this is one of those ones where you could still use the cast diagram, but actually I'd feel happier probably with a graph for this. 3x in this case. Well, when is sine x equal to 1? Remember what the sine graph looks like? We're doing that, so in the range 0 to 360, it's only equal to 1 there. Just at one time at 90 degrees. But this is 3x, so in effect we need to look around the cast diagram 3 times. We've got to go up to 1080 degrees, because that's 3 lots of 360. So we need to keep looking. The next time that we would have it up there would be at 450. Another 90 plus past 360 that is. And then the last time it would do it would be at 810, which is just after 720. And then it wouldn't do it again before we get to the next stopping point. So we're going to divide through by 3, 30 degrees, 150 degrees, and 270 degrees. That would be the 3. Aha, there we go. Just 2 marks for that one. Remember, we can check these in my calculator at the end, so we can try doing sine of 3 times 150 and make sure it gives us 1. Whoa! 4 cos squared theta equals cos theta. Now, I hope that somebody did this wrong. Because a wrong first move would have been to say, aha, let's divide through by cos theta and get rid of the cos theta from there and say 4 cos theta equals 1 and solve it from there. Why would that be a wrong move? Why can't we just divide through by cos theta? Seems sensible. Anybody? We can't do it. Why? What do you think, Ben? Why can't we do it? Because it's like a quadratic, we can't just divide by x. What is the reason for that? Why can't we just divide by x if it's a common factor of both sides? There must be a reason why we can't just go around dividing by cos theta in this case. Because it's what? Nobody think? What we're going to do is we're going to rearrange it, aren't we? And put it equal to 0, and then we're going to factorise it with a common factor of cos theta. If we take cos theta out as a common factor, then we've got cos theta being 0, or 4 cos theta minus 1 being 0. Now can you answer the question why we couldn't just divide by cos theta? Alright, we'll come back to it. So if cos theta is 0, what values of theta does that give us? Yeah, we might be best looking to the graph. What values do we get from cos theta being 0? Well, that's 90 and 270. And this one gives us cos theta is a quarter, which again we need to go back to our calculator and do inverse cos of a quarter, which gives us 75.5 degrees. What's wrong? Okay, cast diagram it. This was cos and it was positive, so our angle is going to go in there and there. 75.5, 75.5, and it gives us 75.5, and the next value around to here would be, what is that this time? 284.5. And just because it's a nice thing to do, we're going to end the question by writing them in ascending order, because I like doing that. Is anybody willing to suggest why we can't just divide by cos theta at the start of this equation? Why we can't just divide by x at the start of the quadratic? Ben?
Taking the solution off.
That's it. As soon as we divide we mustn't divide by something that could possibly be equal to 0. And so we can't divide by the variable just in case it's equal to 0. And in this case, the variable, cos theta being equal to 0, provided 2 of the solutions of our equation. So it would have been a really bad move to have divided by it. We can't just divide by something that could possibly be 0, because that causes us problems. We lose solutions. So that's it. You had to factorise rather than dividing through. Great. That was 4 marks at the end of that. There's probably, if you get to this factorised quadratic, that's 1, and then another 2 for recognising that these are the 2 equations you're solving, and then 2 for the solutions at the end. Okay? Question 2. Now, question 2, we maybe last week hadn't talked about this enough. Find the maximum value of the function f of theta is 4 sine theta minus 20 plus 2. State the smallest positive value of theta for which the maximum value occurs. Well, actually, this isn't. We don't need to get too hung up about this. Sine of something. What can you tell me about maximum and minimum values of sine of a function? What's the biggest value that sine can take on, John?
The highest value on the sine graph is 1.
It's 1. Exactly. The highest value on the sine graph is 1. We're timesing, so the biggest bit that can take is 1. We multiply it by 4. 4 times 1. Oh, should I do my calculator? No. 4 times 1 is just 4. And then we're adding 2 to our answer. So the maximum value is just 6. That's it. When does it occur? Well, the sine graph does that, doesn't it? And its maximum value occurs at 90 degrees. So this has its maximum value when we're doing the sine of 90 in there. In other words, when theta minus 20 is equal to 90. And that would be when theta is 110 degrees. And so that was the answer to the smallest positive value of theta for which the maximum value occurs. And there's your 3 marks. And that's maths.